This is fascinating and a great question. In an organism like this slime mold here, what would we expect to see some kind of competition between nuclei? So this is all one single cell. Everything that you see here that's bright yellow, it's all one single cell, and it contains hundreds of thousands, if not in this specimen's case, millions of nuclei. And what is the competition here like? What happens when one of them gets some kind of advantageous trait? Or one of them falls behind, or what happens in these situations? And you would expect that we would see competition and there'd be intense evolutionary struggles here going on, right? But actually, in most cases we don't observe this. In most cases, in a species, in a social species like this, cooperation is much more powerful than any kind of competition. If you can gain a competitive edge to multiply your nuclei more for of your specific genetic strain, it does not give you much of an actual advantage in the long run. And in most cases, we can follow the logic of why if we think about it a bit. So, if you consider there's a very important balance between the number of nuclei and the number of other organelles in a cell. If say one nucleus started rapidly dividing and disrupting the balance, and there was just too many nuclei to other organelles in the cell, it would be kind of similar to what we see in like cancer, where that would become more of a burden on the cell, and it wouldn't be able to keep up with this rapid growth of just this one organelle, the nucleus, where the other nuclei were not able to keep up, and the other organelles were not able to keep up. And that's just one example of this, but there's actually a lot of other cases. There's a paper. This paper details actually in slime molds. This is a different slime mold, Dictyostelium discoideum. It's a cellular slime mold, not a true slime mold like Physarum polycephalum, the bright yellow one that I just showed you. That one is called an acellular slime mold. They're a little bit different just in some of their nature. Dictyostelium discoideum actually is mostly just an amoebal cell with one nucleus per cell for most of its life, and then when conditions are met, those single cell, single nucleated amoeba come together and form this like slug. I get a picture of that too. Okay, here they are, these little slug things. They crawl around and they form stalks that then have become fruiting bodies and let out spores. I'll get a picture of that. Yeah, here you go. These are the stalks. These were just formed by those little slugs going around. They have a special name. I don't remember what it is though. These little slugs. And these slugs are aggregates of all of these little amoeba coming together and forming, a lot of them form the stalk, some of them form this structure at the top here, and only a smallish percentage of them actually become the spores that are released to become the next generation. And so you would think to yourself, if some of these cells got an advantage, got a competitive advantage over some of the other cells to be more likely to become spores, then you'd think those ones would rapidly take over because they have this huge edge, right? This really isn't the case, though. In fact, here's back to the paper. So this paper called that concept. Now, it's a concept because, importantly, they have never seen this in nature. They have never found Dictyostelium discoideum cells that have this particular trait, where they're more likely to become spores than any of the other cells. They've never seen it. In order to test this, they had to take a specimen. Well, okay, I'm getting ahead of myself. They call these obligate cheaters, and they exploit the partner cells. That's the idea here. In a chimeric organism, in this case, in the case of these slugs, this like temporary organism, if you will, that form these stalks and release those spores, these obligate cheaters would be built to exploit the other cells to form the stalk for them, to release their own genetic material and put that out to form the next generation. But this paper studied this concept, and they had to obtain the strain that had this, apparently advantage on the surface. It looks like an advantage. They had to obtain that strain from a different experiment altogether. It was not a natural strain, and it just didn't have the ability to form stalk cells, right? And I'll show you the data. This is what they found. The The actual height of the entire sporulating body went down pretty drastically as the proportion of this cheater cell population went up in the slug. Isn't that interesting? And they propose in the paper that this might pose a pretty substantial a decline in the likelihood of these spores being widely dispersed. Just even this, height difference of 1 millimeter to 3 millimeters could be a big deal for spore dispersion. And they're suggesting here that as you increase the proportion of the cells that just want to be spores and they're refusing to form the stalk and be helpful to the rest of the organism or the rest of the species, as the proportion of those cells increases, you have this decrease in the height and therefore the overall fitness of that strain of that and even actually the species itself. The fitness goes down quite a bit for that specific genetic trait, and so we don't see it. That this is their theory for why we don't see it in the population. And this is a great example of, in this case, where we have a social creature where you'd think that a trait that exploits others in its species would become advantageous to it, but the moment we see any trait like that appear and start to propagate, it very quickly gets squished, because these are not meant to be competitive around each other directly. They're supposed to be cooperative. Isn't that so fascinating? Humans are famously also a social species, and this does feel like something we've lost touch with a little bit, doesn't it? But cooperation is so much more powerful in most cases than competition. Now, anyway, we have something to learn from slime molds.